Alright, another thing that can help us sometimes when trying to find zeros of a polynomial is something called Descartes' rule of signs. This is named after René Descartes, who I assume discovered it. It has to do with the relationship between the coefficients of each term in a polynomial and the number of possible either positive or negative real zeros that the polynomial could have. What it says is two things. First of all, the number of positive real zeros equals the number of variations in signs of the coefficients of p of x, or is less the number of variations by a positive even integer. That's very confusing. We'll talk about it in a second. It says the same thing about negative real zeros. The number of negative real zeros equals the number of variations in signs of the coefficients of p of negative x. So we have to evaluate that polynomial for negative x, or is less the number of variations by a positive even integer. Let's look at an example of that, because that's a super confusing definition. For example, here's p of x. It equals x to the fourth minus 2x cubed minus 2x squared plus 3x plus 1. Notice there's a positive here, there's a negative here, there's a negative here, there's a positive here, and there's a positive here. And so if we count the number of times the sign changes, well, it changes once, and then it changes twice. And so that means there are either 2 or 0 positive real roots, because Descartes' rule of sign says there's either 2 real roots or less a positive even integer number of real roots. So a positive even integer is 2 or 4 or 6. And so 2 minus 2 would give me 0. So I have a possibly 2 or 0 positive real roots. There's no way that I could ever have more than that, which is the kind of the most important piece of information we get from that analysis. Now, to find the number of possible negative real roots, we do the same thing, except now we first have to evaluate the polynomial for negative x. So when you do that, you end up with x to the fourth plus 2x cubed minus 2x squared minus 3x plus 1, right? And so if this is confusing to you, just know that if you have a negative, if you're trying to evaluate for negative x and you have an odd coefficient, the sign will change. If you have an even coefficient, the sign will not change, because negative times a negative is a positive. So the number of sign changes here, right, we had, this was positive, positive, negative. There's one negative, doesn't change, then it changes from negative to positive. There's another change. So again, we have the 2 or 0 negative real roots. And so putting that all together, what it tells us is that we could have 2 positive and 2 negative. Okay, we had 2 positive, 2 negative. We could have 2 positive real zeros and 2 non-real zeros, so like complex zeros. We could have 2 negative and 2 non-real, or we could have all 4 complex, because we'd have 0 positive and 0 negative. They'd all be non-real. Okay, so that might not seem super useful, but it can be useful. It's particularly useful when we find that there are 0 or 1 sign changes. So here's an example. How many and what kind of roots might this polynomial have? F of x equals x cubed plus 2x squared plus 3x plus 5. Well, it's already evaluated for x, positive x, and all of these terms are positive. So there are no sign changes here in the positive x. That means there are 0 positive real roots. And so if we combine this with the other thing that we know how to do, which is the rational zeros theorem, we could say, so for real quick, p is plus or minus the factors of 5, right? So 1 and 5. And q is plus or minus 1. So p over q is only plus or minus 1 or 5, okay? And so what that means, if there's 0 positive real roots, it means it can't be positive. So the only possible rational roots of this, rational zeros of this polynomial are positive 1 and positive 5. So I ruled out half of my possibilities. It doesn't seem so drastic for this problem, but for other kinds of problems it could be. Now, we also know that if we evaluate this polynomial for f of negative x, so f of negative x, that'd end up being, because if you do negative x times negative x times negative x, it's negative x cubed. We'd still just keep the positive 2x squared. We have negative 3x plus 5. This means that we have, okay, this is negative, positive, negative, positive. So we count the number of sign changes here. We have 1, 2, 3. So that means there are 3 or 1 negative real zeros. So let me quickly sketch what this says. Okay, a cubic function, generally speaking, a cubic function follows a shape like this. We also know, and we'll talk about this more later, that because this is a positive leading coefficient, that it starts in the bottom left and goes to the top right. Okay, so that means if there's no positive real zeros, that there's only two possible things that could be going on with this graph. It could do this. It could cross the x-axis on the negative side once, or it could cross the x-axis on the negative side. Cross the x-axis on the negative side 3 times. It cannot, under any circumstances, do something like this, where it crosses and it has positive roots, because we know there are 0 positive roots, so this couldn't be, right? So there's all sorts of implications to Descartes' rule of signs in conjunction with the fundamental theorem of algebra and the conjugate zeros theorem, because the conjugate zeros theorem says, right, if there was one negative real root, then that means there'd be one negative and two non-real. And those two non-real roots, well, there's the real one, right? And then where are the non-real ones? Well, they're not there, right? You can't see them, okay?